Okay, we're back. We got a camera now. All right. What types of IMFs are found in each of the four is what we kind of left off on. And so all I have here, just wrote them all down. And we're going to start what type of IMFs they have. Just go ahead. Everything has LDFs. So don't have to think about what it is. Everything has London dispersion forces. And we're not ranking which one is the highest or anything yet. We would use their masses for that. But everything has London dispersion forces as their first force. For the second one, we have to determine if they have dipole-dipole forces. So all we need to do is if it's polar, it will. If it's non-polar, it won't. First, I have CH4, made entirely of carbon and hydrogen, so it's non-polar. So I don't have dipole-dipole forces. pH3, if we drew out its Lewis structure, would look like this. Oops, that's an H. Okay. It would have some polarity in it. It would have some dipoles pointing towards the phosphorus here. And these two would cancel out, but this one wouldn't. So this one is polar. So because of that, it has dipole. I'm just going to abbreviate it to save time. CO2. Okay, it has some dipole forces, it has some dipole moments in it, but this time they cancel out. Because they cancel out, there's nope, this is a non-polar molecule, and there are no dipole-dipole forces. Lastly, I have HF. Dipole moment towards the fluorine, and these have dipole-dipole forces. The last one is hydrogen bonds. So all you're looking for is if it has an H bonded to either an N, O, or F. This has an H but is bonded to a C. This has an H is bonded to a P. This doesn't have an H. This has an H bonded to an F. So this one has hydrogen bonds. And that's what you're doing. The hardest one to determine is definitely if it's polar or not, but we learned how to do polarity, and hopefully we're all experts or approaching expert status on figuring out if something's polar or not. It's very important. Okay. So those are the types found in each of those. And here it says arrange the following from lowest to highest expected boiling points. All right, so we have 5 more atoms here, and we just want to arrange them from lowest boiling point to highest boiling point. So what we're looking at for a question like this is their total intermolecular forces. All right. So I'm going from lowest to highest boiling point based on their total intermolecular forces. So my atoms, H2, are my molecules, C2H6, H2O, NH3, CO. All right, so we're going, which ones have the highest? So all of them have London dispersion forces. So I find it easiest to start backwards. The way I would do this is first look at how many hydrogen bonds something has. The more hydrogen bonds you have, the greater your IMF should be. So more H bond equals more IMF. And if you have more IMF, you have a higher boiling point. So the only two I see that should have hydrogen bonds are these two. Because you have an H bonded to an N, you have an H bonded to an O. But if you look at the number of H's bonded, this one has 2 of them, and this one has 3 hydrogen bonds. So hydrogen bonds. All the other ones have 0. This is the most important, the strongest intermolecular force. So because this one has 3 hydrogen bonds, this one's going to be number 5 overall, because we're going from lowest to highest. So this one will be the strongest, the highest boiling point we should expect. And this one should be number 4 then, the next highest one we expect, because they have the most hydrogen bonds. Now with the tie between all of those, we can go to the next force, is dipole-dipole forces. These first 2 will not have dipole-dipole forces because they're made entirely of hydrogens and carbons. These 2 we don't really care about anymore. They would have dipole-dipole forces because hydrogen bonds are types of dipole-dipole forces, but they don't really matter, so we don't really have to worry about those. Carbon monoxide looks like this. It is polar, so it has dipole-dipole forces. And those are kind of the next strongest one, so I'm going to call this one number 3. This one should be higher boiling point than these 2 because it has dipole-dipole forces. Now, everything has London dispersion forces, but what we need to compare here is which one has more London dispersion forces. So I guess number 2 over here should be is, or are, grammar, dipole forces present. And then 3, you're just going to pair which one has the more London dispersion forces. We know they all have them, but which one has more? And I'm comparing these two atoms. This one, C2H6, is definitely has more molar mass, so I know it has more London dispersion forces than H2. So I know this one, H2, is number 1. It's the weakest, lowest boiling point, and then C2H6 would be number 2. And this is kind of our process we use. Hydrogen bonds are the easiest one to find. The more hydrogen bonds, the more intermolecular forces you have. So that's why I chose NH3 as my highest boiling point, H2O is second. Then number 2 is a little bit trickier because you have to look at the molecules, what they look like, determine if there's any polarity. If dipole-dipole forces are present, like they are for CO, okay, then it'd be next. So dipole-dipole should be stronger than London dispersion force, typically. And then once you get to just London dispersion forces, you just rank them based off their molar masses. This one has more London dispersion forces because it's larger. This one has less. So that's why I made this one number 1, this one number 2. All right, so this kind of summarizes this again. To determine the greatest intermolecular forces, and therefore the highest melting and boiling points, use the following as a general guide. Number 1, the most H bonds has more IMFs. Number 2, if tied, or 0 would be a tie as well, polar molecules have more IMFs than nonpolar molecules usually. And we'll get into this with our practice, but this is our general trend we follow, but like we kind of been saying a couple times, really large molecules, it might throw it out of balance. Right? Intermolecular forces we have a general sort of idea we follow with them, with relative strength. So a lot of times questions will ask you, like, explain why this thing has more intermolecular forces than this thing. And then we have to apply this knowledge in that way. And we're going to do a bunch of practice with that, so don't worry. But that's kind of the most common way you see it. And then 3, if multiple non-polar things exist, the more massive ones usually have higher IMFs. Okay, so now we want to explain why Br2 is a liquid at room temperature, but a polar molecule CO is a gas. So there's kind of a lot here. So let's break this down. So we're saying Br2 is a liquid, but CO is polar and it's a gas. So if we're thinking about their intermolecular forces here, okay, bromine only has London dispersion forces, right? Br2 is just Br bonded to a Br, so it's not polar, and there's no hydrogen bonding. CO, we just drew that one, it's carbon monoxide, is polar, so it has London dispersion forces and dipole-dipole forces. But the question says, explain why then. Why is bromine a liquid? Liquid implies, right, if we're thinking about melting points, okay, the temperature you melt at, it's saying this one has a higher melting point because it takes more energy to melt it. Or I really should have said boiling point because it's turning into a gas. But like this, the trend follows as a higher melting point and boiling point. Okay, this one hasn't boiled yet, so we're not at a high enough temperature to reach its boiling point. CO is already boiled, right? So that means it must have a lower boiling point because it's already a gas. Okay, but that doesn't really add up with what our trends were just saying, because we're saying this one has a higher boiling point, so we would expect it to have more total intermolecular forces, but it only has one type. Carbon monoxide has both of these types, so shouldn't it be stronger? This is a very sort of common type of question here. So what you need to do is list out all the intermolecular forces, and then we're going to say this. We're going to say Br2 has a higher boiling point. Therefore, it has higher IMFs. Okay, that's kind of the same relationship we've been using, but backwards. Because it has a higher boiling point, it must have higher intermolecular forces. Okay, so this means the London dispersion forces of Br2 must be greater than the London dispersion forces and dipole-dipole forces of CO. Okay. So this means that London dispersion forces, that's the only force it has, must be stronger than both of these collective forces of carbon monoxide. And the reason that it is because Br2 is a pretty large molecule. So Br2 weighs significantly more than this. So its LDFs are greater than the LDFs of CO. But because it's so large, not only are its LDFs greater than just CO's LDFs, they're greater than these two things added together. So if you add together the dipole-dipole and London dispersion forces of carbon monoxide, the London dispersion forces by themselves of Br2 outweigh that still. And that's what this explanation kind of says. So the question is basically telling you that this is true, right? It's saying that the forces total of bromine must be higher than the forces of this because it has a higher melting point, because it's still a liquid. And so this is our explanation for why, right? Br2 has a higher boiling point, therefore it has higher IMFs. That's basically what the question's saying. This means the LDFs of Br2 must be greater than the LDFs and dipole-dipole forces of CO. Okay. If it asks us to kind of explain why, you could say Br2 is more mass, or no, you don't want to say that. Okay. You want to say Br2 has a more polarizable electron cloud. That's a fancy way to say it. So for formal FRQs, you shouldn't write this kind of trick that bromine has more mass as our explanation. You should say this is the explanation, but just know that more polarizable things have greater mass as well. Okay, so that's kind of a lot for now, but that's what we're kind of working towards with these two chapters, being able to answer questions like that. All right, now our last little section here is about solids. Ionic and metallic solids, we're going to talk about them a little bit, a few things we need to know about them. All right, many solids form crystalline structures held together by intermolecular forces. Now, when you have a solid, in general, the molecules don't move very much. So if you think about most solids like the paper you're writing on, the molecules are held in place. They're not moving anywhere. Now, compare that to a liquid, those molecules can kind of move around in sort of that solution. And that's really the main, chemistry difference between them, is that solids, they're stuck in place. If you add enough energy to a solid, though, those molecules start to vibrate. That energy can't just disappear, so they start to vibrate around. And if you add way too much energy, if you keep adding more and more energy, the molecules will overcome the attractive forces holding them in place, and they will turn into a liquid. So if you think about ice molecules, you have H2Os. In ice, these molecules are not allowed to move. So all these little dashed lines are the attractive forces holding these things in place. Now, if you add energy to this ice cube, right, these molecules are going to start to vibrate back and forth, right? And if they start vibrating fast enough, eventually they'll be able to break these bonds, and then they're free to move around, right? So as you add heat, these things are starting to become free to move because they break the intermolecular forces. And that's what liquids are. Liquids, you have the same exact atoms, except now they have enough energy to slide past each other. They can bump into each other, right? Bump off of each other. And that's what's happening in a sample of water. Even water that looks perfectly still to us, these molecules are free to move around and they're bumping into each other, right? Even if it looks perfectly still to us. In an ice cube or something, in a solid, that can't happen. All the molecules are held in place. Right. And there's a lot of other properties that kind of change as a result of that, but this mainly is just looking at how to melt something. Right. All you have to do is add enough energy to the molecules that they're no longer held by these forces and able to slide past each other. To freeze something, all you got to do is do the opposite. You got to slow these molecules down enough that when they start to slow down, these forces, they're next to each other for a little bit longer, and if they slow down too much, then they're going to be held in place by that sort of force there. And the same thing, you could also go to be a gas. We'll talk more about that later. But to boil, you're kind of doing the same thing. Boil, okay? When these molecules, they're all kind of held together in place, like a water droplet or something like that, right? Water molecules aren't absolutely free to go wherever they want. But if you boil them, they are. So if you give these enough energy, they're going to leave their puddle, right? Maybe this one's going to be able to go like way over here. This one will go like way over here, way up here. If they're able to leave, then they're gases. And gases move completely independently around their rooms, and they don't really care about each other at all. All right, but you have to give the molecules enough energy so that they're not held together by those hydrogen bonds or whatever else is holding them together. Solids in general have a rigid structure, meaning that they don't change. They're kind of boring and stay the same. They have a fixed volume and they don't do much. They're the lowest energy molecules, and the molecules are held very tightly in ionic, metallic, molecular, and covalent network solids. Those are all different types of solids that we're going to talk about. If something is a solid at room temperature, that means it has a relatively high melting point and has not melted yet. Metals and nonmetals tend to make ionic bonds and join together. So we talked about ionic bonding, but these are what the actual structures look like. Ionic solids are made from a cation, which is a positive charge, and an anion, negative charge, combined together that form a lattice complex. So that's kind of the most important idea with ionic solids is you have this pattern, negative, positive, negative, positive. Or if you go down, positive, negative, positive, negative. It makes this checkerboard pattern. And the reason why is this maximizes all the attractive forces. Imagine you're like this sodium atom here. You're surrounded on all sides by negative charges that you really like. But what if you're this chlorine atom? You're surrounded on all sides by a positively charged thing. So this structure is very, very solid and hard to break. There's all sorts of positive electrostatic attraction going on with this structure. And this is what ionic things look like. Like imagine like a salt crystal. It's like a repeating pattern through the entire thing of positive and negative charges called a lattice complex. So to kind of describe this, we know a little bit about bonding, but sodium wants to lose an electron to make an empty octet. So sodium we have over here, it wants to lose its one valence electron to get down to 0 to be satisfied. Chlorine is the opposite. Chlorine has 7 valence electrons and it wants to gain one more. So we put the two together, they'll react to satisfy the needs of both. Sodium gives that one electron over to chlorine, so sodium has 0 valence electrons, chlorine has 8, and they now are both ions. The sodium has a positive charge because it lost an electron, chlorine has a negative charge because it gained an electron. The ions would be attracted to each other and form an ionic solid. And now for this entire thing, you can imagine this happening over and over and over again with sodiums and chlorines that are next to each other. Now, with other atoms do this too. Magnesium wants to lose 2 electrons, magnesium right here, and oxygen wants to gain 2 electrons, so they can make a similar sort of deal. They react and make MgO. Magnesium gives 2 electrons to oxygen, so this time my ions have charges of 2 plus and 2 minus, because they've lost or gained 2 electrons, respectively. So now, if we're thinking about their solid that they make, would we expect that solid to be stronger or weaker than NaCl? Okay, so the only thing we're changing is now the charges are double or twice as strong. So yeah, that makes the solid a lot stronger. You're basically doubling for each of these, so quadrupling more or less, those attractive forces, right? These charges are bigger, therefore they're more attracted to each other. And this solid, MgO, we'd expect it to have a much higher melting point. You'll need more energy to break apart that ionic lattice structure. Now, MgO has a higher melting point than NaCl because the force holding it together is stronger because it has greater charges. It takes more energy to break the lattice apart. Now we're going to do another comparison of NaCl and NaF. So NaCl or NaF, with both of these situations, both things have a 1 plus and 1 minus charge. Chlorine and fluorine have the same charge, but the only difference is F is smaller. So F is higher up on the periodic table, therefore its atomic radius is smaller, which would you now predict to have stronger intermolecular forces or intramolecular forces, depending how you think about it. Okay. And now NaF would be a little bit higher melting point than NaCl. Smaller atoms are able to get closer to each other. So the smaller the atoms are, the greater the force of attraction between them. So it takes more energy to break them. Now that's not a huge amount more. Here we have their boiling points. NaCl boils at 801 degrees Celsius, and sodium fluoride with that slightly smaller fluorine atom is 996. So it goes up a little bit because of the smaller atom. But if we look at the thing with positive +2 and -2 charges, MgO, that boiling point is like way higher than the other ones. Okay? So having higher charges or smaller atoms will make your lattice stronger. But the higher charges is kind of the dominating factor there. The greater the magnitude of the charges, the stronger the lattice is. And this is by far the most important factor. But if they're tied, if they're the same charges, you can figure out which one is expected to be stronger by looking at the ion size. Smaller ions will also increase the strength of the lattice, just not quite as much. The strength of a lattice is called lattice energy, and lattice energy is kind of defined as how much energy it takes to break apart that lattice. The higher the lattice energy, the greater the melting and boiling point of that salt. Okay. Predict what ionic compound could be made from these two things, and then predict which one will have a higher lattice energy. Okay, so we have magnesium with fluorine. We have calcium with oxygen. So the first thing I need to do is find both their charges. Magnesium is in that second row, right? So it has 2 valence electrons or a 2+ charge. Fluorine needs 1 valence electron, so it has a 1- charge. These are their oxidation states. Calcium's oxidation state is 2+, oxygen's is 2-. Calcium wants to lose 2 electrons, oxygen wants to gain 2 electrons. Magnesium wants to lose 2 electrons, fluorine wants to gain 1 electron. When you make compounds of these things, you swap those charges. Mg gets the 1 from fluorine, fluorine gets the 2 from magnesium. And the compound these would make, the ratio that these things need to bond in is MgF2, which kind of makes sense. For these numbers, they need to kind of cancel out. So I need 2 fluorines because each of them can only gain 1 electron and have 2 electrons to gain, which is why we kind of flip the numbers like that. With CaO, right, the numbers are already even. So you can flip the charges the same way and get Ca2O2, but that just kind of simplifies to CaO. Now, that kind of makes sense, though, because if you just have one of these and one of these, they already bond perfectly, right? This wants to lose 2, this wants to gain 2. So you don't need to have 2 of them for this to happen. They can just bond with a single one. So our 2 compounds we make are magnesium fluoride and calcium oxide. And now I want to predict which one will have the higher lattice energy. And for that, we just kind of look at what they're made of. This has a 2+ charge and a 1- charge. This has a 2+ and a 2-. These have higher magnitudes, right? The 2s would cancel out, they'd be the same, but the 2- is greater than the 1-. So I'd say this has a higher lattice energy. And if it didn't ask us, but it would also have a higher melting or boiling point. All right, some properties of ionic compounds are all explained by their lattice structure. If a lattice structure shifts, even by 1 atom, so let's kind of look at this. We're taking this picture, we have a sharp blow, right? I'm hitting this with a hammer. And if I'm able to shift this lattice structure by 1 atom, this attraction pattern falls completely apart, right? Because now I shift this down 1, the positives are next to each other, these negatives are next to each other, these positives are next to each other, and that's all bad. Those things are going to repel each other a lot. And because of that, ionic structures are brittle, meaning if you smack them with a hammer, they're going to break all apart, right? Because if you're able to give a sharp blow to the lattice structure and shift it even by 1 atom or by more atoms, then the whole thing is going to break apart. Disrupting the lattice makes the structure fall apart. So if you're able to shift it just a little bit, the whole thing just disintegrates. Okay. Oops. Next, we have conductivity. Electricity is the movement of electrons through something. Ionic solids are rigid, and the electrons have no way to travel through them. Okay, so here I have two electrons. They're trying to meet each other on one side or the other, but there's just no room for them to kind of fit through this very solid structure. The ions in this this solid don't move. Because of that, electrons can't move through it. However, if you're taking this salt and dissolving it in water, or putting it into the liquid state in some way, then they become good conductors of electricity. And to kind of show that, I have this picture here. Here's an ionic solid. The ions fixed in a lattice cannot move, right? So if I'm trying to move an electron through this, right, there's nowhere for it to go. If you have a molten or aqueous solution, then now your ions are free to kind of move about as they want. And because of that, your negative charges can move towards the positive terminal, your positive charges can move to the negative terminals. The ions can now move, and therefore they can conduct electricity. In a solid, the ions are stuck in place, they cannot move, therefore they do not conduct electricity. Now, metallic solids have some similar properties as well. They're made from one or more metals. They don't form sort of traditional bonds, which is why we don't really talk about them very much. We're talking about bonding like atoms together. But they have their own special sort of type of bonding. Now, all metals want to lose electrons, but they don't have any other metals to give those to, right? Non-metals are things that gain electrons, and metallic bonds is only metals. So instead of giving their electrons away to something, they do something interesting with them. They all give up all the different metal atoms that are bonding together, give up their valence electrons to get down to zero, and then those electrons just kind of float freely between them into a collective sea of electrons. Okay, so I kind of have the ideas shown here. So over here on the left, we have a metal that has one valence electron, maybe it's silver or something, right? So maybe these are all silver atoms with one valence electron. Each of them is a positive charge now because they've all lost one electron. And these electrons are free to move around as they see fit. So they kind of move, and they're all being shared into like one big sea of electrons. If something like maybe you have iron that has two valence electrons, each of these would now be a 2+ charge atom because they're each giving up 2 electrons. And then these electrons that you see are free to float around as they want. The metal ions are all happy because they've satisfied the octet rule. Their octet is empty. And now you kind of have all these positive and negative charges to kind of vibe together with each other. And they can move around as they see fit and are attracted to each other. Okay, metals have a few different properties, and they're all explained by this sea of electrons. It's the one unique thing about metals that you don't see in any other type of bonding. So any question about the properties of a metal comes down to their sea of electrons. Metals are shiny, and this is because they have free electrons floating around. That free sea of electrons can lead to the photoelectric effect and make light, produce light. Metals are also good conductors of electricity and heat, but mainly electricity is what we focus on, because these electrons are free to move throughout that sample. Unlike in an ionic solid that is held in place, these electrons can just move wherever they want. And that's what electricity is. It's the movement of electrons through an object. And metals are malleable, meaning they can bend a lot without breaking. Right? They aren't brittle like an ionic thing is. If I was to smack this with a hammer, okay, it wouldn't really care. Right? I can mold and bend its shape around because it doesn't have to be in a specific pattern. Right? This glue, right? These electrons act as a sort of glue and basically hold it all in place. So if I was able to smack this with a hammer, it wouldn't care, right? Metals can be strung out really thin into wires and still be pretty strong. The fancy word for that is ductile. They can be beat out into sheets, right? Very, very thin. They don't really care. They can be molded into all these different shapes because of their unique structure, right? It doesn't really matter exactly where these atoms are. They're still just attracted to each other and free to move about as they want. Alloys are combinations of different metals together. Now, we've done some work with some alloys before. We talked about brass. Brass is an alloy made from copper and zinc together. There's two main kinds of alloys that we're going to talk about: substitutional alloys and interstitial alloys. The names come from the type of alloys and what they look like. So a substitutional alloy might look something like this. Now, I have this for you in your notes, but it printed in black and white, so you might not be able to tell. Okay, but with this picture, it's easier to see. Alloys, substitutional alloys have multiple types of metals that are about the same size. This alloy, for example, is 75% red metal and 25% blue metals. Each blue atom is completely replacing where one of the reds would have been. And this is a substitutional alloy. You can imagine if this was pure red before. I'm just picking out full metal atoms and replacing them with a new one. This is the most common sort of alloy that you'll see, and this is what like brass is. You can say all the red are copper and all the blue are zinc. You have multiple different metals that are about the same size of each other, replacing each other. An interstitial alloy is different. You have all metal, all the red ones here are the same atom. Maybe it's iron, for example. And all these tiny little green ones are much smaller atoms that kind of fit in the gaps between the metal atoms. And that's where interstitial, inter meaning between, stitial meaning kind of space. So these are atoms that go in the in-between space between larger atoms. So these will usually be things like carbon or oxygen or smaller nonmetals that are much smaller than the metals that kind of fit in the gaps and can change their properties. And just know that means it's interstitial. So if we're trying to describe this alloy pictured here, okay, we have 3 different colors going on. So what you would say is that the red and blue, right, the blue are just replacing red atoms. So this alloy is substitutional when you're thinking about the red and the blue together. But the green are going in the gaps in between the red and blue atoms. Because of that, this alloy is also interstitial. So this would actually be a version that is both. This alloy is substitutional, the blue atoms, and interstitial, the green ones. All right, now to kind of finish up the day, we have a couple of smaller topics, and these are things I don't think are incredibly important. We'll do a little bit of work with them. There's a few other types of solids, and they're all covalent bonds that are solids. Usually covalent things are liquids or gases because they don't have a ton of intermolecular forces or ionic bonds or metallic bonds or anything like that. So, but there are a few that are solids. So we'll talk about those. I think these are less important, but I'm just going to give you a few examples. A molecular solid is I2, iodine. Now, iodine only has London dispersion forces, but because iodine is so big, it has so many London dispersion forces that it's actually a solid at room temperature, right? Iodine atoms are so big that they have such a polarizable electron cloud and so many electrons in it that their total intermolecular forces makes them solid at room temperature. So this is kind of, over here is what the molecule would sort of look like. All these atoms are just kind of held in place because there's so many London dispersion forces. And this is a picture of what iodine looks like in real life. Okay, some more covalent solids are carbon and silicon atoms forming large complexes, things like diamonds, silicon dioxide, silicon carbide, graphite. They're long carbon or silicon chains forming really large sort of complex molecules. These are very strong solids. They are very hard to break or melt or do anything to, and they only form under specific conditions, sort of things. So like diamonds, you've definitely heard of, for example, they are very, very hard to break, or they have an extremely high melting point, and they don't really fall apart very easily. Okay. 3-dimensional shapes like diamonds have high melting points and are very hard to manipulate because the fixed structure is very durable. These are held in place by covalent bonds, right? These are not dashed lines here. So this over here, this diamond structure on the left, right, is very hard to break. You have to break full covalent bonds, which are, remember, stronger than intermolecular forces. Now, 2-dimensional shapes like graphite, this is what graphite sort of looks like. You have all these ring shapes. They're actually stacked on top and layered on top of each other. So this actually has a couple different types of forces. Each individual sheet is made of covalent bonds, but the individual sheets held together are only attracted to each other through London dispersion forces. So you can actually like rub off one of these sheets pretty easily, but the sheet is hard to break itself. So like each layer is hard to break, but you can remove the layers from each other pretty easily. Okay. Each sheet moves independently, allowing you to rub off graphite in sheets, and that's what happens if you're using a graphite pencil, right? As you're going across the paper, sheets of the layers of the graphite molecule are falling off relatively easily, right? Graphite still has a high melting point. If you try to burn your pencil, it wouldn't really burn because each individual sheet has all these covalent bonds that are a lot harder to break inside of it. So to melt this, I would actually have to separate all these atoms from each other, which would mean breaking these full bonds. And same thing with the diamonds. To melt this, I would have to break all of these bonds so that the atoms are free to move around as they want. All right, and that's it. So sorry for the weird pause in between. Today we talked about intermolecular forces. Let me go back over here. Sorry. Okay, we talked about intermolecular forces and a couple things about solids. There's a few more types of solids that are not that important, but we'll talk about a little bit more in class. The main ones today, I want you to know about metals and ionic solids, and then all about intermolecular forces. Let me go back here to the front, kind of going forward. So this one goes kind of hand in hand with chapter 8. We'll be talking about intermolecular forces a little bit more and how they affect liquids a little bit. All right, have a good day, everybody, and I'll see you soon.